Hello friends, good afternoon and welcome to Reset Live Lectures. Dear friends, today in chemistry we will be in phase equilibria talk about phase diagram of two component systems. To discuss this topic we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is assistant professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome sir to our studios and request him to start the lecture. Welcome sir.
Hello, welcome. Dear friends, let me welcome all of you to this continuation lecture of phase diagram of two component system. Till the point of time we have seen in phase diagram of two component systems that when two solid components are mixed and they are brought to some elevated temperature, they form a liquid mixture, and when they do crystallize from their liquid mixture as just two components without undergoing any chemical reactions, such kind of such kind of systems are called simple eutectic systems, because it is one fixed composition at fixed external pressure, which becomes the composition at which both the components are in saturation solubility composition, and they are saturated with respect to each other. And in that situation, neither of the component will allow the other one to crystallize separately, and they will both crystallize from the liquid mixture simultaneously in that situation. And when this is so, such a mixture would behave as if it is a pure compound. And now we would like to shed little more light on such phase diagrams as to how we can go about to draw the phase diagrams, or if we have the phase diagrams for a two component system having simple eutectic systems, then how we can interpret what it would have been, how it would have been drawn, and what kind of analogous systems we can think of. So with that viewpoint, let us have a look at this. We all know that cooling curves, method of cooling curves has been very useful for drawing phase diagrams. So over here also we will make use of cooling curves. So we can just have a look at the cooling curves for pure compounds as well as eutectic mixtures and the other mixtures to it as well. This particular cooling curve is just nothing. This is the A cooling curve, which is just nothing but the temperature versus time graph, and it is very clear from this cooling curve that point B here represent the halt temperature. At this halt temperature, you would observe a start of freezing of one of the component whose amount is in greater quantity, whose presence is in greater quantity in the liquid mixture compared to saturation solubility composition, and its crystallization will continue till point C is reached. Here we can see in the cooling curve, up to the point C you will observe continuation of the crystallization of that particular component which is present in extra amount compared to saturation solubility composition. And at point C, when the system reaches the point C in the cooling curve, as per the cooling curve, now you will start observing the simultaneous crystallization of both the components. That is because now both the components are in saturation solubility composition. So now neither of these two components will allow other one to separate as such, and therefore whenever such simultaneous crystallization of such a mixture occurs, that occurs leaving behind the remaining liquid having the same composition as that of the crystals which continue to form. So therefore since the composition of liquid and the solid substance which crystallizes, which freezes from that liquid mixture is been the same. So, you will observe a constant in the temperature during the crystallization, and that is because of the fact that when due to crystallization heat gets evolved within the system, that same quantity of heat is rejected to its surrounding while cooling, and therefore, the temperature of the system remains constant in this way. When complete crystallization of both components A and B occurs, thereafter you will observe again a cooling. But now it is important to note that the ability of a solid substance to reject to transfer heat to surrounding is lesser compared to a liquid substance. So, therefore, you will observe the rate of cooling pattern which would be different from the rate of cooling pattern of a liquid mixture when only liquid mixture was getting cooled. Having said this, now we would like to stress upon a very important point. This is the phase diagram for simple eutectic system, where this axis represent the pure component A, on the other side this axis represent pure component B, and the whole x axis over here represents the composition of the mixture, which lies from component A 100% here and 0% to the B point side, and component B at B point side is 100% and at component A is 0%, and somewhere in between you can complementarily draw the axis, divide the axis into 10 equal compartments indicating 10%, 20%, 30%, 40%, 50%, 60% and so on up to 100% of that particular component at which the axis is reached, and the one particular axis represent a point B. For example, over here this axis represent pure component B and this axis represent pure component A. Now, what I want to stress upon is that suppose if you have a liquid mixture, if you have a mixture for example of two pure components A and B, and you have mixed in some proportion such that you can say it is 75% with respect to component B and 25 with respect to component A. Now, it is very clear that 75% component B would be very close to axis B, because axis B represents the axis on the composition axis at which component B is 100%. So, therefore, you can see this point which is the point which comes from drawing perpendicular from point C. When you draw perpendicular from point C onto composition axis, this point now represent the composition of the liquid mixture, and this point is very close to 100% component B here. So, as a result we can see this point, and when we divide it in equal 10 compartments, we will get over here as 75% component B. Having said this 75% component B is because it contains more amount of substance B or component B compared to saturation solubility component, or in other words we can say that component B is present in extra amount compared to saturation solubility component. So, when this liquid mixture from point C is allowed to cool. Now, how it is allowed to cool, it is very important to note that when we have, suppose for example we take a boiling point and we add to this is benzoic acid and urea for example, and when we in a proportion that benzoic acid is 7.5 gram and urea is 0.25 gram. So, if urea represent component A and benzoic acid represent component B, then it is very clear with 7.5 gram benzoic acid it means 75% by weight of the mixture, which has been there, that is represented. Now, that mixture when is heated and such that both the urea as well as benzoic acid gets melted. So, it would lead to formation of a liquid mixture, and when that liquid mixture is heated at some elevated temperature. So, what we will do is we will get the overall state point on this. This is the phase diagram of these two component system. Now, in this phase diagram, this point C over here, this represent now this at this point of time represent the overall state of the system. That is, we have a boiling point that is our system in which contains 7.5 gram benzoic acid and 2.5 gram urea, and the overall state point is represented by point C. Now, what happens when you allow the system to cool? What happens? The overall state point of system moves downward. You can see over here this line segment CL, this line segment over to the composition axis, this is a vertical line, and since it lies only at one point of the composition axis. So, it means if all the points on the line segment, this vertical line segment, if they represent the overall state of the system, then it means all the points on this line segment lies on one curve which lies only on one particular fixed composition of system, and that is the reason this kind of vertical line is called isopleth. And more importantly, I would like to draw upon your attention that any point in this phase diagram also represents a particular state of the system. So, right. So, when we have a liquid mixture of urea and benzoic acid as I described earlier, and if the overall state point of the system is represented by point C, and then when we let this boiling tube or the system be cooled, then it will transfer heat from the system to the surrounding, and during this process, when the system would be transferring heat to the surrounding, its temperature would decrease. So, you can see overall, since solid substance and the liquid mixture would not have this very high appreciable vapor pressure. So, its composition over this entire process, in this entire process would remain same. So, therefore, you will the overall state point of the system will only go downward on this line segment, and ultimately first of all it reaches a temperature. Let us say that temperature on this phase diagram correspond to this point L. Now, at this temperature what will happen? This is, suppose this is one temperature at which you have reached the temperature at which crystallization of first crystal of B starts. And it is important to note that the temperature corresponding to point L is lesser than that corresponding to point B. That is, this liquid mixture will have freezing point lower than that of pure component B, and more importantly its melting point is also lower than that of pure component A. Right. Having said this, at point L, therefore, first crystal of substance B will appear. Now, interestingly, we have a line segment over here which is nothing but a horizontal line. Now, that horizontal line is nothing but LS. This is point L, which is the terminating point of this line segment LS, and this point S also represents the terminating point of this line segment LS. So, on this point, on this line LS, there are 2 points. This point L coincides with curve BE. If you watch it very if you closely watch it, this curve BE, this represents the freezing point curve and also called Liquidus curve. If you remember, in our previous lecture we had said that this curve is called Liquidus curve because it represents the composition of liquid phase which is in equilibrium with the solid phase at which first crystal of that solid substance do appear. So, it means this point L represent the composition of the liquid phase. this point L represent composition of the liquid phase. Now, since first crystal of substance B has already appeared, so what would be amount fraction of substance B in that solid phase? Because that solid phase has only one substance, that is substance B. Therefore, its amount fraction will always be unity, or in other words it would be 100% B. So, therefore, this line segment LS meets the axis B at point S. So, therefore, this point S represent the composition of this solid phase. So, now you can see this line segment LS is a very important line which connects the two different phases, because this curve BE, above curve BE there is only liquid phase, and on axis B here the point S in particular at this point in this phase diagram, you can see this represent the pure component B, which is 100%. So, this point also describes the composition of solid phase. So, this axis which represent the solid phase and this curve BE which represent the liquid phase, and this line segment LS connects these two curves, this axis curve or this curve BE. So, therefore, LS is a length of line segment or a line segment which connects the two different phases over here in the phase diagram. These two phases are solid phase and liquid phase. So, therefore, this line segment can be called as tie line. As you can see, it ties two points which are presented on curves corresponding to liquid phase and curve corresponding to solid phase. So, this curve BE therefore is also called the Liquidus curve, and it is important to note, I said that earlier also, that this point L is basically represent the amount fraction or the percentage composition of a particular component either B or A in the liquid phase, and that is why this curve represent any point on the curve BE also represent the composition of the liquid phase, and point S therefore represent the composition only of the solid phase. Now, this it is important to note that you can see overall state point L do coincide with this point O. This do coincide with this point O, and point O is the overall composition. You can see point O represent the overall state point of the system at this temperature, and this coincides with point L. This same two points are describing this point, same two variables are describing this point. It means these 2 points do coincide at point L. At point L there is the 2 points O and L do coincide on this line segment. So, this means that since only a first crystal has appeared of the solid substance B, so it means practically on the overall composition on the liquid phase there is not much change, and therefore, the composition of overall system just coincides with that of the composition of the liquid phase. That is why point O and L do coincide over here. Point O is the name of the same point here, point L is also the name of same point here, whereas point O determines the composition of the overall system and point L do determine the composition of the liquid phase, right. If what we try to do now is, if we try to further cool the system, because you know that when some first crystal of B appears from it, then the remaining liquid will have a composition in which relative amount of B would be little bit extra, will be in little bit extra amount. So, therefore, it would lead to further depression in freezing point of component B, because component A is now in relatively little extra amount. So, therefore, this would lead to a decrease in melting point of or freezing point of further crystallization of component B from this liquid mixture, and therefore, as you further decrease the temperature, what you observe is that if our overall state point now moves from this point O, the earlier point, to O dash. So, now if we have you may note over here that upon further decrease in temperature you have reached the point O dash. Point O dash now represent the overall state point of a system. It is of importance to note that this point O dash does not coincide with point L or L dash. So, what does it mean? And more importantly, I would also like to let you appreciate the point that I have shown over here. This square box which is grey in color represent the overall state point of system. The all grey color represent all the liquid phase, and just a small white dot basically represent this first crystal of this solid substance B. Right. Upon further crystallization, few more crystals do come up, or these crystals do grows, that is amount of solid substance therefore continues to come in the solid phase, and accordingly you can see in this pictorial view that this little bit extra gray amount, why this extra this rectangular box, square box now is shown in little bit with more intensity of the color. That is because of the fact now component A is in relatively extra amount in this remaining liquid. So, since component B is been shown with the white color, so when crystallization of component B continues, so obviously it would lead to increase in intensity of the color in the square box. That would mean that proportion of component A, relative proportion of component A in the relative mixture is continuously increasing, and proportion of component B, or you can say amount of component B in solid phase, is continuously increasing. That is why you would see 1, 2, 3, 4 crystals, and even in bigger size crystals being shown over here in this square box, which represent the pictorial view of the overall state point of the system. This is only for the indicative purpose, right. So, overall state point of system now is given by point O dash, and now since it does not coincide with point L dash, now L dash is a point which lies on the Liquidus curve or the curve BE, which represent the liquid phase, or in other words the composition of the liquid phase, and point S dash now represent new composition of the solid phase. It is important to note that when crystallization of component B continues, then what you will observe, relatively the proportion of component A increases. So, now the composition of the remaining mixture will continue to shift towards pure component A, and that is what is we can note it from the same observation we can note from here also. The point L dash lies very close, lies more close to the composition axis of corresponding to pure component A. On the other hand, overall state point lies somewhere in between, and the overall state point of the solid phase lies at the same component B axis, that is S dash now. So, you can see one more important point is that amount of solid substance B which appears in amount of substance B which appears in solid phase now is continuously increasing, and amount of liquid phase is continuously decreasing. These two observations are important to make a note of, that is amount of solid substance grows during solidification or during cooling, and amount of liquid substance continues to decrease, or more importantly the proportion of component A increases in the remaining liquid and the amount of substance B continuously increases. And what is happening over here in the phase diagram also on this line segment. Now, not the LS but L dash S dash is the length of line segment which represent a line segment which connect the two different curves, Which are these two different curves? These are Liquidus curve and Solidus curve. So, again we can say this point, this line segment L dash L dash L dash S dash is a tie line, and it connects now the composition of two different phase, that is L dash represent the, if we draw a perpendicular from point L dash onto the composition axis, we can easily note the composition of the remaining liquid, and point S dash is simply denote the composition of pure component B in the solid phase, that is 100% component B, or in other words the amount fraction component B equal to 1. So, there is a very important rule, that is called lever rule, which relate the relative amount, that is number of moles of the solid phase and the liquid phase. That we would also like to stress upon, but for the time being let us now talk about overall state point of the system when more and more of solidification occurs, or in other words when you have a even lower temperature. When you continue to cool the system, its temperature further decreases, and now suppose the overall state point of the system has reached from point O dash to O double dash. Now, you can see over here this point O double dash, again it is important to note that it does not coincide with point L double dash, which represent composition of liquid phase, or in other words it also not moreover it also not coincides with point S double dash, which represent composition of the solid substance. Right. Having said this, therefore, one thing is very important to note, that the length of line segment from O dash to S dash or O double dash to S double dash is constant. However, length of line segment from O dash to L dash was lesser compared to length of line segment which represent the from point O double dash to L double dash. Or in other words, O dash L dash length is lesser compared to O double dash L double dash length. What is the reason for this? Can we make some analogy? Can we make some parallelism, or can we draw some conclusion out of this observation? And that conclusion is basically summed up in terms of a very important rule, that is called lever rule. So, we will discuss about this lever rule, but the point is that before we talk about lever rule, it is important to note that any two terminating points on the tie line represent the composition of two different phases. So, with this discussion we would lead to discussion of phase rule in the subsequent modules. Thank you. Alright, so in this module let us have a discussion of the lever rule. Prior to the discussion of lever rule, let us further make a little bit more understanding of when we cool the system, what goes on within the system. So, you can see on this point O double dash, which represent overall state point of system, if we further cool the system, its temperature will decrease. It is a quite obvious observation. So, it means overall state point of the system, which is now represented by point O double dash, with further go downward, and what will happen is that ultimately it would reach to point OE. Now, it is very important to note that what is this point OE? Point OE is just nothing but the overall state point of the system when the temperature has reached the eutectic temperature. If you remember, we had a discussion of the fact what is a eutectic composition. Now, since you have withdrawn so much of solid substance B from the liquid mixture, so that this continuous crystallization or solidification of component B has led to a remaining liquid whose composition just reached the saturation solubility composition. It means now the liquid B is saturated with liquid A and liquid A is saturated with respect to liquid A. Having said this, now therefore, they are in saturation solubility composition. As I said earlier, they will crystallize together in the same proportion as they are present in the liquid phase. So, therefore, at this point OE, now this point E represent the composition of the remaining liquid and this point SE represent the composition of the solid phase. So, it means that whatever the liquid phase now remains will continue to crystallize, and ultimately when last trace of liquid, and this crystallization will continue at constant temperature, and when last trace of liquid also gets crystallized, this square box would therefore represent here the pictorial representation of the state of the system. You can see the whole black color in this square box represents solid substance A, whereas whole small white color patches and this big patches of white color do represent pure component B. So, therefore, complete crystallization of solid B occurs at OE, and therefore, at any temperature below OE you will have only solid phase. And you can start with any composition. You can start with this composition, or you can start with this composition, or any other composition. Ultimately, any point which lies on this curve ESE, this would represent the overall state point from which crystallization of only eutectic mixture would occur. And you can see thereafter complete solid phase existence occurs. It means this is point E represent the lowest temperature, or OE also, which represent lowest temperature at which a liquid can exist, below which there is only solid substance. It means this is the least melting point of a liquid mixture. The least melting point if a mixture has, because this is the pure substance B which has higher melting point, and this point represent the melting point or freezing point of liquid mixture which has little less proportion of B. When you decrease the proportion of B further, this point therefore now represent the start of solidification of or melting point or crystallization temperature of that liquid mixture composition. When you further decrease proportion of component B, then this point, and if you decrease the proportion of component B such that it reaches component point E, now this point E represent only the composition of the liquid mixture which is called as the eutectic mixture. As you can see, if you would have started from this point, this point here which is being represented by the pointer, this point, if it is represented by this point, now if you decrease the temperature, now if it continues to go down, it reaches point E. So, eutectic mixture of a liquid mixture which has saturation solubility composition has a cooling curve of the kind, the one that resembles that of a pure component, where a long uniform cooling pattern is being observed, that is a straight line is first observed, thereafter only a constant in temperature, and once again the temperature decreases. So, that is what you do observe. So, now it is important to note that we will talk more about what is the role of this eutectic point, or how we can make use of this eutectic temperature or eutectic mixture to design some cooling mixtures. But for the time being, it is time now to understand what is lever rule. Now, as I said, when you continue to decrease the temperature of the system, the amount of solid substance increases and amount of liquid substance decreases. Now, if we talk about length of line segment, the length of line segment OL or O dash L dash or O double dash L double dash is increasing, or in other words, from the overall state point O dash or O double dash, if you draw a line from overall state point to the liquid phase, its length increases. That is why OL dash is lesser in amount and O double dash L double dash is greater in amount. So, it means relatively, if you see the length of line segments, if you compare from O to S or O to L, the length of line segment from O to L is continuously increasing, and length of line segment from O to S is continuously is almost remaining same, but we can say relatively is decreasing relative to OL line. So, what does mean? It does mean there is parallelism also. Let us have a look at this. As you decrease temperature, amount of substance be continuously increasing and also increasing the length of line segment OL. So, here we have a lever rule which says we can compare the amount of substances, both A, B or whatever is present in a particular phase, that is total number of moles in solid phase to total number of moles in liquid phase. If we take the ratio of the two, that is equal to the ratio of the length of line segment OL divided by OS. OL you can see is continuously increasing as you decrease the temperature, and OS just remains constant. So, therefore, now what is increasing? The amount of substance B in the solid phase, and that is why OL, which also increases, represent amount of substance in the solid phase, and OS represent the which almost remains constant, but relatively its length of line segment decreases. So, it represents the number of moles in the liquid phase. So, we can easily obtain from this phase diagram, that is the ratio of number of mole of solid phase to number of mole of liquid phase, which is equal to lengths of these two line segments OL and OS. When the overall state point is O dash, this ratio is equal to O dash L dash, and when this ratio is represented by overall state point O double dash, then this ratio is represented by O double dash L double dash, O double dash S double dash. So, this is what is lever rule. Lever rule basically is a simple rule which is a ratio which relates the ratio of length of line segments from the overall state points to the two different phases which are connected by the tie line on which the overall state point lies. This ratio is equal to the ratio of number of moles of the chemical substances which are present in these two different phases. That is what we have from the lever rule, and therefore, lever rule helps us in identifying also, if suppose we have a solid substance which is in equilibrium with its liquid mixture of A and B, then we can, if we have the value of solid substance, number of moles of solid substance, then we can easily determine how many number of moles are present now in the liquid phase, remaining liquid. If we just have the values of lengths of line segments, which can be easily obtained by a scale or from this kind of a phase diagram. So, lever rule is therefore very helpful in determining the number of moles of different components in the remaining liquid or in the solid phase, if we get to know from this. So, lever rule is therefore very helpful in identifying such observations. right. Having said this, eutectic mixture therefore consists of two or more substances and having the lowest freezing point of any possible mixture of these components. The minimum freezing point for a set of components is called the eutectic point or eutectic temperature. Low melting point alloys are usually eutectic mixtures. We will discuss about a tin cadmium phase diagram we will make use of. We will get to discuss what way this alloy helps us to carry out soldering process in the electronic industry, right. Having said this, but before we do that, let us make another observation. You see, you would have seen in the cooling curve, if first of all what used to happen, when you have a solid substance which is in greater quantity, much greater quantity, suppose you have a mixture of A and B, and in this mixture of A and B, if you have compound B whose presence is in much greater quantity compared to the saturation solubility composition, or in other words, suppose this is the point, T5 is the point which represent here the composition of the liquid mixture, which liquid mixture you are trying to cool. And while cooling, from the cooling curve you will observe first from a higher temperature, first you will observe a uniform cooling, then at temperature T5 you will observe a alt and then non-uniform cooling, and ultimately up to temperature TE you will get a non-uniform cooling, and then thereafter you will get a constant in temperature, and then thereafter, or in other words the arrest in temperature, and thereafter just the rate of cooling pattern would be little different, but a uniform rate of cooling will be observed. So therefore, what you can do is you can plot is the length of this line segment or this tie line from this liquid composition which you were trying to cool. This length of line segment you can note, and you can plot this length of line segment here on this composition axis from 0 to 100, A to B, and on this y axis it should not be time, it should be the length of tie line, or it should be the time. If we are saying time, it means time of constant in temperature in the cooling curve. So, I try to show you the cooling curve as well, so as to make an analogy. If you see it very carefully, this is the cooling curve for a liquid mixture in which huge quantity of component B was there and very small quantity of A had been mixed. First uniform cooling, then non-uniform cooling, and then constant. This constant line, or in other words the time during which constant in temperature occurs, this is small. If you have more amount of component A being added to component B, so liquid mixture contains is more close to saturation solubility, then this uniform cooling pattern occurs to a greater time, and then thereafter non-uniform cooling, and more importantly, because the component A is now richer, in other words the liquid mixture is richer in proportion of component A now, this time corresponding to the earlier mixture for which this cooling curve was plotted. So therefore, you will reach the saturation solubility composition much earlier, and therefore, since you will have more number of moles in the remaining liquid which represent the saturation solubility composition. So therefore, this length of line segment which represent a constant in temperature, or in other words the time during which the temperature remains constant of the temperature of the system remains constant, that will increase. So what I am trying to say is, if you plot the time during which the constant in temperature occurs with this time with the composition in the overall system which you had taken. So suppose you had taken a composition of liquid mixture corresponding to this point, it will give you lesser value of time for which a constant in temperature occurs, and you can see it over here represented by 5 parenthesis figure 5. And now when you have this kind of a liquid mixture which is represented by temperature T4, here this point if represent the overall composition of the liquid mixture which you try to cool, then it starts freezing here and it continues its freezing and reaches this point which represent the saturation solubility composition. Now, at this point you will have more more time at which constant in temperature occurs. So, you will plot this time, you can see this is time versus composition axis, you will plot this time on the composition axis for which you had started with the liquid mixture which you were trying to cool. So, from this side also, if you have a T1 corresponding liquid mixture, it will have a different time which is you have plotted over here. On this its composition, if you start with a composition of system 2 which starts its crystallization at temperature T2. So, it will have greater time of constant temperature in comparison to mixture number 1. So, therefore, this time continues to increase, from this side also it continues to increase, and there is a maximum time. There is a mixture which is called eutectic mixture, which is the mixture which has a composition corresponding to saturation solubility composition, and therefore, component A in this mixture is saturated with respect to component B, and component B is also saturated with respect to component A. So, this mixture has a saturation solubility composition and would not allow any of the component to crystallize separately, and therefore, both these components will crystallize together in the same proportion as they are present in the liquid mixture remaining liquid. So, therefore, only a uniform cooling and then thereafter a constant in temperature, and therefore, you will see maximum amount of time will be there for such a mixture which will undergo cooling at constant temperature, because here only crystallization or cooling occurs during which solidification occurs at a constant temperature. So, this system 3 would represent such a system and would be called eutectic mixture. So, it is important to note eutectic mixture is that mixture of both the components which crystallizes at constant temperature over a largest time compared to any other liquid mixture. So, this is a very important point to make a note of. Eutectic mixture is characterized by its cooling pattern or cooling curve, which is very similar to that of a pure component. Suppose urea, its melting point is 121 and 128, and benzoic acid melting point 121. Their cooling curve do resemble, but the point is that constant temperature occurs at 121 for benzoic acid and 128 for urea. On the other hand, here for the mixture, eutectic mixture of these two components, the constant in temperature would occur at minus 76 degrees Celsius, which is much lower than that of any of the two components. So, therefore, what I am trying to say is this mixture is the one which melts at a least temperature, that is needed to be given less amount of heat. So, that is easily melted. So, in Greek I also pointed out to you the earlier also that, so in Greek we have a word for it, EUU means easily, and TCTIC means tactic, means melting. So, in this Greek word eutectic, which comes from Greek language, basically it conveys the meaning as a mixture which melts easily, that is easily melting mixture, and is called eutectic mixture, and temperature at which such a mixture melts is called eutectic temperature, and eutectic temperature is the least temperature at which melting is observed. Right, having said this, we have also discussed lever rule and very important observation about eutectic mixture. Here it is now time to discuss the applicability of phase rule on this system. Now, let us consider various points. As I said earlier, any point on the phase diagram represent the overall state of the system. This point C represent the overall state of the system in which a mixture is present only in one phase, liquid phase. I told you earlier also that this curve AE represent liquidus curve or liquidus curve for component A, and curve B represent liquidus curve or liquidus curve for component B, and above curve AEB, therefore, there is only one phase, that is liquid phase, liquid A and B mixture. Now, at any point below curve PER, below this straight line PER, therefore, is only solid A and solid B, any point below this line. And now this point BE, this curve BE represent a locus of all the points at which crystallization of a particular different composition of mixture starts, and curve AE represents start of solidification or start of freezing or freezing point of different liquid mixture having different compositions in the same manner, and point E represent eutectic point. At eutectic point, since we have both the solids, so we have two solid phases and one liquid phase. So, at eutectic point you have three phases in equilibrium. At point A you have, since only one substance you have, so which is present in liquid as well as solid phase. So, you have at point A two phases. Similarly, at point B you have solid substance B in equilibrium with its liquid phase. So, therefore, there is two phases again for point B. Any point on curve BE, there is solid B in equilibrium with the liquid phase, that is liquid mixture or melt in other words. So, here also you have two different phases. Any point on curve AE also represent liquid mixture in equilibrium with but now this time with solid A. So, therefore, any point on this curve AE also locus of all those points represent curve AE, therefore, also represent locus of all those points which represent the overall state having two different phases. Now, as you have seen earlier during our discussion also, any point within this curve BER represents solid B in equilibrium with liquid melt or a mixture of A and B in the liquid phase. Similarly, curve area bounded by curve AEP also represent two different phases where you have liquid phase or melt or liquid mixture of A and B in equilibrium with the solid A. So, it is very clear therefore, now where you have one phase equilibria, that is all the points above curve AEB represent liquid phase, therefore, represent one phase equilibria, and any point below curve PER therefore represent two different solids. So, therefore, this represent two phase equilibria, and any point within this area bounded by curve BER, this is a two phase equilibria. Any point on this curve on this area represent two phase equilibria, which means one solid phase, that is B in equilibrium with melt, and area bounded by curve AEP represent again two different phases, but now liquid mixture with in equilibrium with solid phase, but now this at this point of time solid phase is solid A. Having said this, now let us apply the phase rule. What is phase rule? That is a simple equation which relate the number of component, number of phases and degree of freedom. So, here component, since we are discussing only phase diagrams of two component system. So, we have only two components A and B. So, C is constant here, C is 2, and P can be different at different points on the phase diagram. So, C minus P plus 2 is phase rule, general phase rule, and since we were discussing systems which are present at constant temperature, that is constant pressure, because we were dealing with only open systems where we had a boiling tube, where we had added two solid substances, we had heated them, we had brought to elevated temperature in the liquid phase, and thereafter we did this cooling. So, therefore, this whole system was maintained at constant pressure, because the system was open to atmosphere and the pressure of atmosphere was exerting on the system. So, therefore, its pressure always remained constant. So, we therefore specified the value of pressure. So, therefore, we made use of 1 degree of freedom. So, therefore, we will decrease 1. So, that phase rule which is lesser in 1 degree of freedom by 1 because of specification of one of the variable, that is namely the pressure. So therefore, that reduced phase rule here we will apply, and that reduced phase rule is that F equal to degree of freedom equal to C minus P plus 1. C over here is component P, the number of phases, and F is the degree of freedom, or in other words the variance of the system also. That is how many variables you can vary without producing any change in the state of the system. Having said this, now let us apply first of all to the area bounded by curve AEP. AEP is this area. This area contains, as I just described, contains two components, two phases and degree of freedom 1. If we substitute in this C and P value in this phase rule equation, the reduced phase rule, we will get F equal to 1. It means we can have vary only one variable, that is either we can vary temperature or we can vary composition. That means if we specify the composition within this area, if suppose this is the point where the pointer stands, this represents the point which represents the state of the system, it means you have fixed its composition. When you have fixed its composition, it means at this composition you will have a particular liquid and vapor phase composition and a particular value of temperature. Or in other words, if you fix temperature, then from that temperature you can draw tie line, and then it will let the composition of the two phases as fixed. Same argument, with same argument we can say degree of freedom, number of component phases are also same, C2, P2 and F1 in the area bounded by curve BER. And now in this area below curve PER, there is only solid A and solid B, so therefore there are two phases. So P is 2 there and C is already 2, we have already discussed. So degree of freedom is 1. It means you may specify, you can only vary the temperature, the composition always remains same. That is the composition of amount fraction of component A in solid phase is 1, solid phase B is also 1, and similarly any point within the area above curve AEB, there is only liquid phase, so 1 phase, 2 component. So therefore 2 degree of freedom you can vary both temperature and composition. With such description of phase diagram, we had discussed the phase diagram of two component system with simple eutectic systems. So our attention will be the discussion of phase diagram of two component system, which involves congruent compound formation or incongruent compound formation. More importantly, we would also discuss the application of the simple eutectic phase diagram also relating to the soldering of alloys in electronic industry and freezing mixtures. So these two applications are also important, that we will take up in our next lecture. Thank you so much.
Dear friends, on that note, we would like to thank Dr. Kumar for coming to our show and delivering this wonderful lecture. And thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.